So today's lab is about spectrophotometry, or Beer's law. So we are going to use a special instrument that measures the intensity of the color of a solution, and we're going to use it to determine the concentration of color in an unknown solution. So this is Beer's law. Beer's law is this equation, and it tells us that the absorbance is directly proportional to concentration. If we increase concentration, we increase absorbance. And we can see that if we plot absorbance versus concentration. Okay, so we get a straight line here. It's linearly correlated. The higher the concentration, the higher the absorbance. So here's the pieces for Beer's law. Absorbance equals, this is a constant, times another constant. This is actually related to how big our little cuvette is. This is the little piece of equipment that we put our sample in. And the key is that absorbance is linearly correlated with concentration. And that correlation comes from this factor. So what are we going to do today? You are going to make up a series of colored solutions. We're going to use a cobalt chloride solution that's red in color, and you are going to make a series of concentrations.
I didn't get that. Could you try again?
I think I'm realizing when I say the word series, she picks up. Okay, so you are going to make a series of that's it. So you will make a collection of solutions that have different concentrations, and hopefully you can see here from this picture that they run from having no colored solution to basically an intensely colored solution. And one of the things that's interesting is you may not notice any difference in the color of these by your eye, but our instrument will be able to tell that there's a difference in color. So this is probably going to be the most time-consuming portion of the lab, is actually making up this collection of 8 different solutions. But once you have that collection of 8 different solutions, you're going to measure the absorbance value of them, and then you're going to plot absorbance as a function of concentration, or actually we'll show you how to have the little instrument that we have do it for you. And importantly, you're going to be interested in the slope of this line, because if we think about the slope of a straight line, y equals mx plus b, what we're going to have is the slope is the piece that linearly correlates the absorbance with the concentration. Now maybe you know that the equation for a straight line is y equals mx plus b, but we're going to have that when there's no color in our solution, the absorbance is going to be 0. We're going to set up our instrument so it knows that. So this b value, this y-intercept value, is actually going to be 0, so we pretty much can ignore it. So on the next few slides, you're going to see the equation is y equals mx. Okay, so the second part of this, so the first part is really making this what we call standard curve. The second part is actually using that standard curve to figure out how colored an unknown solution is. And everybody's going to have their own unknown, or I should say you and your partner will have your unknown. And the question is, there's a certain amount of redness to this solution. Is it a light red, a medium red, a dark red? And you're going to use your standard curve, and you're going to use the absorbance of your unknown, and you're going to use the equation from your standard curve. You're going to plug your absorbance in here, and we know the slope from your standard curve. That's why we made our standard curve, and then we're going to be solving for this x value, which is your concentration. Now, one other thing to highlight here, it's possible that you might have a standard solution that's too red, too concentrated, so you need to dilute it. But you want to make sure that you don't dilute it too much and get something that's not red enough. So if something is too dilute, you're going to have an absorbance value that's too low, and it's not going to be within the range of where your line is. Similarly, if you have something that's too concentrated, you're going to have something with too high of an absorbance value, and it won't be within the region of your standard curve line. So sort of the Goldilocks situation here is we want to have just the right amount of redness so that it falls within this range. So if your solution is too red to start, don't worry. Just dilute a little bit. We'll walk through exactly how you're going to do that dilution, but you want to get it so that you get to a redness that is just right, and it's going to fall within the range of where you determined your standard curve. Okay, So last thing to highlight, and then I'm just going to walk through the 4-part steps of what you're going to do today. We need to know what absorbance value we're going to be, or what wavelength we're going to be measuring this absorbance value. So performing a wavelength scan is kind of another way of saying, what wavelength do I want to measure my absorbance at? So you're going to take a measurement of your red solution, but rather than our x-axis being concentration and having a bunch of different solutions, we're going to take one red solution, and then the instrument is going to measure the absorbance at a variety of different wavelengths. It's going to go through the colored spectrum, and it's going to give us a value for the lambda max. It's going to say this is the best wavelength so that you have the strongest signal to measure your experimental data. So that's called performing a wavelength scan. So just as a way to sort of wrap up here and put all of these pieces in order, here's the steps that you're going to do. The first thing that you're going to do when you get into lab is you're going to use your most red solution, that's our concentrated stock solution, and you're going to follow the directions to perform a wavelength scan and figure out what that lambda max is. I encourage you to check with myself or the teaching assistant for the lab and make sure that you are using the right wavelength before you move on to the next steps. The next steps are going to be the probably most time consuming, because you're going to need to make up these 8 solutions. So it's going to take a little time to make those 8 solutions. Follow the directions very carefully when you're making those solutions, because the accuracy of those solutions is going to determine how good your line is. Once you have those 8 solutions, you're going to go and then measure their concentration and use that to generate your standard curve. Importantly, the piece that we want from the instrument after we generate our standard curve is that slope. Once you have that slope, then you're ready to move on and use that information to figure out the concentration of your unknown. So again, you're going to obtain your unknown and you're going to measure the absorbance value of it. Now, if it's something that the absorbance is too high, it's outside the range of where your standard curve is, you're going to do a dilution. Regardless, I want you to do at least one dilution so that you understand how this process works. And what that means is taking 1 milliliter of your sample and mixing it with 4 milliliters of water. So you're going to dilute it essentially by 5-fold. And then you're going to measure the absorbance of that solution. Now, if that happens to be something that's still too concentrated and you're up here, you might need to do one more dilution. But as long as you have one reading that's within the absorbance range of where you did your standard curve, you're good to go. Okay, last thing then is you're going to use your standard curve equation and you measure the absorbance values. I should say we're going to use the one that's just right. You're going to plug that into here. We got the slope, and that's going to go here, and then you have an equation where you're solving for one unknown, your concentration of cobalt chloride in your unknown solution. And that wraps up the lab. There's a few post-lab questions that ask you to think a little bit more deeply about some of these kinds of calculations, but that's pretty much it.